Well, thank you, Jim. I'm going to take this mic here. If it works, yeah, great. So I like to walk around a little bit, so it's a little more interesting that way for me. So yeah, thank you, Jim. I'm excited to be here, and here we go. So what I'll talk about, I mean, this is pretty much, I think, an introduction to the kind of work we do, but also how we think about the problem of using AI in science and engineering. So the tasks that I gave myself, I wasn't really quite sure what but between the lines, this is something you were trying to connect the school and trying to think about how you can, engage in AI in the sciences and engineering. And that's the spirit of what I'm going to talk about, is sort of problems we've worked on and my thoughts on all of this. And I think we have time after the presentation for Q&A as well. So the kinds of stuff I work on is these kinds of multi-scale problems where we try to connect, like Jim said, the nano to the macro. We're really fascinated with looking at cross-scale interactions, something I've been trying to work on, figure out for many decades now. Sort of what happens if you make a chemical change, and how is it going to affect something as big as an Eiffel Tower, or a bone, or a skin, or an organism? And there's many problems in the space, obviously. They're very complex. Actually, it doesn't always work. I don't know why. Okay, well. Okay, wait.
You can find the
He wants to stay on the slide. Okay, here we go. I don't know. I'll switch. Okay. So anyway, so the space, the scale is big. The complexity is large, and this is just sort of a snapshot of what it looks like. So this is a spider web on the left, and at the micro scale, something you can pretty much see with a microscope. And on the right-hand side, you see molecular structure, actually of collagen, but if you were to look at spider silk, it would kind of look like this. So you have water molecules, you have extreme complexity. So the problem for us is a lot of times in materials modeling. I'm assuming that not all of you work in materials, right? You come from many different disciplines of engineering. So the problem is, if you want to design something like this, or even model it, understand it, it's extremely complicated, because these are just two pictures. And you have these many scales in the material that are going to play together to form functions. So for us, a lot of times we're trying to solve this, I think, traditionally using what we call multi-scale modeling. This is the left-hand side. We've spent lots of time on this, and it is sort of the idea that you kind of integrate through space and time by coarse graining, right? Your degrees of freedom, because you cannot solve, let's say, the Eiffel Tower problem using all the atoms, right? So you basically create groups of atoms and groups of atoms, and you kind of do this coarse graining, really through the scales all the way to maybe the continuum scale. The problem with this is that this idea been around for 30, 40 years. It's not really tractable to solve real problems with this a lot of times. And there's a couple of reasons. One is that it's extremely computationally expensive, but also it's not really the best use of our resources, probably because if you think about these, let's say something like a 3D printing process, not every atom matters. And so the question becomes really what atom actually matters, what mechanisms matter. And so the only way we can do this is by human ingenuity, right? Kind of figuring out maybe there are governing laws, maybe we can discover some relationships. But because we don't really know how to do this in most real cases, we're kind of stuck with this brute force computation. And the other reason is that if we do these multi-scale problems and we do coarse grain, we're losing a lot of information. I'll show you a bunch of examples. Like in diseases, you might coarse grain your molecules, and you might actually not model the specific chemistry at the site of a mutation, right? Or the specific mechanism at a crack tip. And suddenly, you can solve the problem, but you're actually missing a lot of the elementary features. And so this dilemma, really got us into thinking differently how we can model this kind of multi-scale problem. And so I'll tell you a little story, kind of how I got to this point, or how we got into this field in our lab, and then we'll talk about kind of the ideas behind it and how we use AI for this. But so this general problem, is something that's around, and of course you can come up with your own problems in your own fields. What we can do now, we can actually now begin to solve these multi-scale problems in both directions, forward and inverse, using what we call generative AI or scientific generative AI or whatever name you want to give it. But basically, these are models that are able to understand some of those physical relationships across scales, across different domains, even of knowledge, pretty well, okay? And so as we get better in modeling systems with AI techniques, we're going to be able to create reasoning engines that can understand a lot of the physics, the chemistry, a lot of different kinds of knowledge, and connect the dots essentially between them. And that's, in fact, sort of how we got into this. Now, let me show you a little bit of a picture of when you hear machine learning, or sometimes people call AI the same thing, but it's really not. But let's say machine learning. A lot of times you see this picture on the left. Conventional models really, they are very good interpolators, but they're very bad in actually making predictions, right? So that's the challenge of, if you say off the shelf, current technology AI, a lot of times is that these models really have no awareness of what they're doing. All they're doing is basically fitting data, right? And so if you want to extrapolate, you can only do so much. And in fact, most models, you limit applying them to kind of spaces in between, maybe existing data, maybe a little bit outside the data. But if you want to go to this space where there's excess, right, something you've never studied before, you can't do this really, right, because there's no data there. So what we're trying to build are machines that can solve this problem. That's sort of what I'm trying to do in my lab, and what community is trying to do as a whole, to build AI systems, artificial intelligence, meaning machines that can think through problems, okay, that can actually tell us something about behavior here in the space in between, or of course, if you think about knowledge, kind of generate new knowledge and push the frontier of what we understand. And that can be done in collaboration with humans, of course. It doesn't mean it's a machine on its own, but it can be potentially. So that's sort of what I will talk about, what I think we need to do and what we can do to get there, and what the opportunities are in this space. So this is sort of a picture. So I'm still struggling with that thing. Here we go. I think it is actually the bad. Maybe it's bad. It doesn't matter what it is. I'll figure it out. But anyway, so this is how we got to this. So basically, I look at problems like these. This is a multi-scale problem, right? What I do conventionally to model this, spider silk, let's say, I basically, I take a look at the Euclidean space of geometry, and I say here's a molecule. I make the molecule a bundle, and I make maybe. And like I said, this is a possibility of doing this multi-scale modeling, except you're missing some details, right? But that's the only way you can really go through the scales. What you actually want to do is you don't want to actually necessarily coarse grain every atom blindly. You want to actually coarse grain things that are not important for the question asked. You want to keep fidelity and resolution for things that matter, right? So for example, a particular sequence mutation or pattern might be really important at a certain position to drive the assembly of silk fibers, right? Or a processing condition. And you can see it's not just about structure, it's about processing, it's about boundary conditions, initial conditions, maybe other contexts as well. So the way we started modeling this, and this is sort of how we got into this field back in 2011, we began to think about modeling something like silk through graphs, right? So instead of describing it in Euclidean space, where you have interactions only close by, and you get further range interactions by integrating over time and space, which is what makes it so expensive, we said, why don't we describe the behavior of these systems using graph methods? And so this is what you see on the right. So we actually started by building these graph-based models. This is an example from sort of general logic, but we did this for materials as well. So you can basically tell a story of why and how something like silk behaves in a certain way. And you capture all these relationships. You might say, I have a sequence, and the sequence is a certain repetitive pattern, but that pattern has to be in a certain range of patterns. But if it's this particular pattern, something really interesting happens, right? So you can kind of capture these relationships between nodes, and other nodes, and then the relationships are sort of the other relationships, I guess. And this could be anything, right? So essentially, it could be a word, an atom, a group of atoms, and so on. So we started building these representations back then, and really, it was quite exciting actually. We did some isomorphisms, sort of showed similar mechanisms of things like resilience between materials and social networks, language and music. And we could do a lot of really cool mappings between graph representations of systems, because you can replace the actual building blocks. So let's say, on the top, you have an object 1, object 2, object 3. It could be many different things. It could be, like in this example, it could be a man, a hair color, and a color. But it could be a tennis ball, a game device, and a device, right? So it could be all sorts of different things. And the relationships between different representations, different actual physical objects, for example, can be mapped. Okay? And you can identify what's the mechanics behind something like robustness, right? And how do you find that? How do you translate robustness from silk into robustness in ceramics, right? This is why we did this, actually. We wanted to see some more abstraction of the modeling process. So, but yeah, we could only do this for really simple toy problems, and actually problems that we knew all the data off. And so this sort of limited our ability to do this. Now, with, kind of modern techniques, we have figured out how to build these graph representations from data directly, in fact, from huge amounts of data. And so everything, so I'm show you just a bunch of different examples here, but and I'll go into more examples and specifics later. But really in a graph, you can kind of capture this graph sort of as a matrix of adjacency. You can kind of say these are the nodes connected in this way. And this particular table would be this graph, right? So you have directions, you have relationships, and you have, lots of different kinds of things you can capture. Not just that there is a relationship, but you can actually also understand what is the relationship, right? It is a tennis ball or it's not a tennis ball or whatnot. And that's how these AI models building work, right? So they build these relationships. And so when you think about this representation, it's quite powerful, right? Because I can digitize lots of different information, from my data. So I can have information where you have atoms, right? So for example, this is an actual graph that I took this screenshot this morning from my models. Let's say you have a bunch of atoms here. So the tokens would be the atoms. And this graph sort of tells me how this atom 175, picking this one as an example, interacts with other atoms, right? And so the actual interaction is not shown here. It's a very abstract representation. It could be a word, it could be some sort of embedding, it could be very different things. But this happens sort of at every layer in the model. So it begins to understand structures of relationships between bits and pieces of information. So now you'll see me mention this actually a few more times with more visuals, but I wanted you to see sort of the raw data, right? So this is actually how it looks. This is the model learns. So and the reason why we do this is we build these, as I mentioned, isomorphisms. So what we want to do with the structural modeling, is actually not to just memorize an answer to a problem. We actually want the model to understand. Yeah, if you conventional machine learning, you do basically nonlinear curve approximation, function approximation. Here, we're trying to build representations of how things actually work. Right? That's the goal, right? So, and then you can do these isomorphic transformations. Like this is actually the example from, from one of the earlier papers. We've done this analytically for converting, understanding of silk to music, and you can build these relationships as a graph, right? This is that. Angles, so hopefully will make sense for all of you in different fields. So here's sort of what the general problem becomes. So let's say I have a bunch of different information. In information, again, it could be, these become the nodes of my graph, right? So it could be an atom in a molecule, it could be an atom in a molecule, but it could also be a variable in an equation. It could be pixels in an image, it could be pixels in a video, right? So all of this becomes my information. So then what I train the model to understand, to do, is to connect the dots, literally, right? So you go from information and you say no. So like say, if you want to ask a question, what is the optical property of this molecule? To answer that question, the model will connect the dots and it will basically think, okay, I have these particular features of each atom, they're connected, there's molecular properties, and all of these things together. This is what we form a constitutive equation, basically, right, for the engineers, to then come up with the answer. And we do this sort of at scale, and then I'll show you plenty of examples, of course, but and hopefully the model will not only have knowledge, make predictions, but also have some outcomes, like predicting what's the next experiment or design or things like that. And we apply this in our work a lot of times in questions like sustainability, clean water, filters, resilient infrastructure. I mean, there's a lot of different things we can build. And all of these problem spaces, of course, are ones where we have huge design spaces and we really cannot just simulate our way out of it most of the time, right? So what you see here is, here's sort of another way to look at this problem. So if I'm too repetitive, let me know, but I think it's sort of illustrative to see. So let's say you're a conventional physics-based modeler, okay? And you want to model plasticity in copper. One of the things I've done back in when I was in grad school, actually. And so the way you do this is you create an inner potential, right? And this is what I've done. We do this all the time. And so you have sort of a relationship, a graph, actually, in fact, of how this atom interacts with another atom. And it could be complex, could be simple, like here's Lennard-Jones potential, but it could be more complicated. And then to solve this boundary value problem, I have to integrate spatially and temporally, right? It takes a long time, lots of computational resources. So what we're saying is, that's great. Again, this graph of having interactions between atoms is great, but maybe there are other laws we can discover of how the system actually behaves, right? So sort of I'm crossing out provocatively, and Jim Bright doesn't like this. I don't like it either, but provocatively, right? I'm crossing out potential and say, hey, you know what? That's not the only way, because basically this is a near diagonal in my graph. It says basically I'm only interacting with my neighbors, but there are relationships in an actual graph that are very long range. And this allows me to say, well, some things are important, some things are not, and this is how they relate. And then I can actually answer a question about a very complex system directly. And I can say, what's the next frame in this movie? And I can actually predict this without having to go through integrating in brute force. So that's kind of like the take I have on this. So that's my platform, kind of where I work from in this field. And of course, this is powerful because the sort of the elementary degree of freedom doesn't just have to be an atom or a molecule or something like this. It actually can be a lot of different things. And so my passion is to really to connect knowledge from different areas, because we believe that if you understand, let's take a look, it's like resilience or toughness. You can understand that in materials, but you can also understand it in social sciences. You can understand it in maybe other fields, maybe computer science, network theory. I mean, there's a lot of different areas. So we think, if we have models that can actually try to understand how these different concepts come together in different fields, maybe you can innovate, you can model, it can be much more effective. In fact, you can actually, we were just talking about this, train a model on data you have, but then you can translate this knowledge into another area, right? Because these graphs, have this property of isomorphism, so they have structural similarities, and all you need to do is to understand that this concept appears in this particular way in this field. I can just simply translate this, and this is what these models can actually do, right? So this is sort of the mechanistic reason why they are so powerful. And so in fact, for us, we want to say, we don't want to throw away thousands of years, maybe hundreds of 15,000 years or so of human civilization. I mean, we've had logic, we had math, of course, calculus, we have numerical solutions, we have data science today. I don't want to choose. So that's my take, right? I don't want to choose to do only data science because, I want to use maybe some physical equations and do some checks on whether I satisfy mass balance or equilibrium, right? So these models actually allow me to do this because my input and my sort of information, right? It can be a number, it can be a symbol, it can be an equation. And those of you who know, category theory actually comes from mathematics, and one of the basic applications of categories is defining algebra, right? The mathematical concept of algebra we know. You basically describe relationships between entities, symbols. And that's what we discover, right? So it's very flexible in kind of what you can feed the model in this way. And this is important. Again, this is sort of those of you probably also, all of you know this, but the reason why we need this is because our problems of design are so gigantic. I mean, you can't even miss we like this example. If you want to design a protein with, let's say, 100 amino acids, you would need actually to make it empirically and build all the possibilities. You would need more atoms than we have in the universe, right? So it's not possible. Clearly. I mean, there are other reasons why it's not possible, but essentially it's impossible to do. So we kind of need to figure out how do we narrow down the search space, right? If you want to design something new. And so anyway, these are the ideas, sort of the reasons why we should get into this. In addition to sort of understanding, of course, fundamentally how the world works. I'm fascinated with understanding how different systems work and how they can be connected and related. But there's also a real practical application like disease. You have rapid aging disease, brittle bone disease, all diseases where you can't average, right? If you were to average the sequence of a collagen molecule, you would miss that mutation that actually causes disease, right? Or in fracture, and this is a well-known problem. If you dealing with fracture problems, this is why they're so hard. In finite element methods, you basically don't have the atomic resolution yet. Fracture is an atomically governed process. So if you really want to figure out how things break and how to make them not break, right? You really need atomic resolution, but this requires brute force calculation. So anyway, these are all motivations, obviously, for why. So now let me talk about the methods and a little more details. So first of all, this is something that most of you work in computation, we track is sort of how much compute is available, and it is true. Compute becomes more available, cheaper. This is the Kurzweil curve, shows essentially, compute becomes sort of infinitesimally cheap. And you can then scale your models, right? So you can build very large models. Other physics-based or data-driven model doesn't matter. I mean, you can build big models and you can see how they scale. And of course, if you make things bigger, you can discover new scaling laws. You might discover that certain size models are able to connect the dots between different areas better. This is particularly true in AI models. And that's where we are, right? So we're kind of at this point where we're getting critical compute to see we can actually build pretty powerful reasoning engines that rival or maybe exceed human capabilities. And this is the reason why we're building these big power plants too, because, or actually should be reactivating them, because you need a lot of compute, right? And so I put this in there. Sometimes people ask me, is it real? I say, yeah, because I mean, here's Microsoft just purchased or leased, I think, let's say purchased the 3 Mile power plant, and that was closed, as you know, since an accident, I guess. So hopefully it's safe now. I think it's much safer now. But they are basically building their own AI. I mean, this is something if you would have that 5 years ago, like crazy, But yeah, it's happening. So and Google, same thing. They I think invested in companies or purchased a company or buying these small reactors. So there are real investments going on to scale. And then, of course, Elon Musk's building big compute clusters. So this is happening all over the place. In fact, you can't buy GPUs anymore because all of these big players are buying them up. So the reason is, in fact, that we have this moment now where we can really ingest all of this different type of data. And here's sort of a more specific example. What can you ingest? Okay, so what are the information, right? The information that we're connecting the dots with. Yeah, experimental data, papers, of course, books, lab notebooks even. Legal documents, protein sequences, obviously. I mean, there's sort of an abundance. I mean, I talk to companies a lot, and one of the things they have is they have technicians that work machines for 40 years and they retire. Well, they have a whole story to tell about how to operate that machine, right? So all of these things can be digitized. So it's not just knowledge that we write in a paper or in a document, but actually human knowledge of various kinds that you can record people, you can video them, you can watch them do things. And all of this can now become these bits and pieces of information that actually can be ingested, sort of eaten by the AI model. And what the AI model will do, it will build these knowledge representations, and then hopefully we'll make some smart things about them. So that's sort of the framework. So it's pretty exciting, actually. And there's the other thing that we like to think about, right? And what we do is that we really don't have. So we have traditionally. I already showed you earlier the conventional machine learning where we do interpolation, I should say. And actually, not just data-driven models, but any other model, right? So PDEs, experiments, anything, they're not really aware, right? So let me explain what I mean by this. So if you take Newton's laws and you apply Newton's laws at the quantum mechanical level, it will make a perfectly fine prediction, but it is wrong. And how do you know it's wrong? Newton's laws do not know they're wrong, right? The equations know they're wrong. You know they're wrong because you compare the prediction against an experiment, or you might have some, right? And so this is actually the first time now that we can build models that can do what we usually do and have some awareness of their own predictions. So what I showed on the right. So this is what we're building is models that can reason. Well, understand physics at a deeper level. So they make a prediction, have a thought, an idea. Yeah, maybe let's use Newton's laws, but actually, let's test this prediction. Let's see if it actually holds up. And if it doesn't hold up, one can go back and actually iterate. So the kind of stuff that we used to do, or we do today, right? So we're beginning to see that AI models can do this kind of stuff. And they can actually learn the process to the answer instead of just learning how to answer, right? So all the models, especially data-driven models, they just memorize a lot of stuff, right? They memorize the answer. And that's why they're so bad in predicting something outside of the distribution of training. Now we have pathways that we're researching that can actually teach models how to reason, how to get to the answer. And of course, obviously, that provides a lot more possibilities for really generalizing things and making predictions outside. So that picture here, I'm going to show this a few times. So basically, in these models that I'll talk about, we're trying to find ways to ask a question, ingest data. Like it might be an image and a question, or it might be an image and asking what's going to happen next. Is this crack going to propagate, or is this protein going to fail, or is this protein going to cause a disease, right? And the model won't just answer and say, yeah, here's my answer, but it actually will answer, it will think about the problem, right? And the answer, and it will go back and iterate, and it will have a structured way of thinking about the problem, the ultimate prediction. And you could be part of that process if you want. If you don't have to be. Sometimes models can be autonomous and they can just sort of figure out solutions on their own. So how do we get there? Well, we get there, I think, because how do we build models like this? And so obviously we're doing a lot of biologically inspired work. Materials we study are usually biological materials, and one of the principles in biological materials, like something like a beautiful flower, is not grown out of one thing, right? It's not a monolithic structure that forms. It actually is made from building blocks, which arrange into building blocks, which arrange into building blocks, and they form, right, this sort of concerted aggregate effect of very complex nonlinear relationships across scales that I alluded to in the very beginning to form something like a flower, which has multiple functionalities and so on. And we can use something like this actually as a paradigm to develop AI models as well. So if you want to build, physics models that can, do these kinds of things, we could start by building with small levels of intelligence, models that can do maybe a couple of things really well. Just like in the maybe in a protein, you can have a protein that's very strong, okay? And then if you combine that strong protein with a functional protein and the binding site, now you create, complex interactions and nonlinear relationships. So same thing here, we're building models that are very good in doing something like, for example, predicting, the stability of collagen molecules, right? So this is one example, right? So we can build a model that can solve actually a very difficult problem, right? Taking a sequence of amino acids and predicting the properties of this protein just from looking at the sequence. And this is actually a very sort of amazing thing, because it's the kind of stuff that we were dreaming about doing for a long time. We couldn't figure out how to do it until we had AI tools to do this. And I show this in a little more detail because this particular model actually is developed based on the principle of what we call pre-training and fine-tuning. And this is something really important, especially for science and engineering, because a lot of times we don't have a lot of data. We have some data, right? So what we're doing here, we're teaching this model something about the problem without teaching it the actual problem we're ultimately trying to solve. We're trying to just teach the model some general understanding of how proteins work. And what we're doing this is actually it could be creative about how you do this, but in this case, we give it a sequence. We have, of course, billions of protein sequences, right? So there's no shortage of sequences. There's a shortage of defining sequences and properties. We have very few. Right? For collagen, we only had a couple hundred actually. So we can take, these billions of sequences and we can basically give this model something to do. And, then we go off on vacation or go home, whatever. But what we're teaching the model to do, we basically say, I want you to look at all these billion sequences. And I'm going to give you a set of these every time I train, so do a training step. And I'm going to cross out 15% of the letters. And again, you could do the same thing in, I don't know, mechanics problems where you give solutions to a problem and you basically remove part of the solution and you let the model learn what was there, right? So what was the amino acid that I crossed out? And so you do this randomly, right? Every time you cross out a different one. So it's a very easy task to train. It requires no supervision, right? The model kind of creates its own problems, essentially every step. And when you do this long enough, actually, over some time, the model has learned how to solve this problem, right? So if you cross out any amino acid in there, it will be able to fill in the gap. You might say, that's totally useless. Why did you do this? Well, I did this because now the model understands something about proteins, right? And I have used very cheap data, available data, unlabeled data. I mean, nobody has labeled these protein sequences. Now I'm going to show the model just a couple of hundred sequences and their properties. Okay, and now the model learns, train further. Now you teach the model, okay, so this sequence associates with this property in this particular way. Right? You don't need a lot of data. So that's the point I want to spend just a few more minutes on this here, because this is something of obviously applicable to many engineering problems. Right? You don't have a lot of data in your domain, but you can teach models sort of general principles. And again, structurally it works because you're really teaching under the hood the model to think in graphs and representations and relationships. The other thing that you see, so this is another example of things we can do. We can even invert the problem. So not only can I predict the properties of protein, but I can actually charge this model to design proteins. That's another really, really hard, actually maybe more difficult problem, obviously. So here we took basically a design objective like predicting, designing sequences that meet a certain structural motif. Let's say you want a protein that looks a certain way, has a certain secondary structure or other properties. This model will design sequences that are candidates that meet that particular design demand. Okay, and so this is done in this particular case using call it diffusion model. So this diffusion model kind of generates solutions. It's like if you run DALI 3 or something like this, but here we're using proteins and molecules. That's a pretty effective way. Again, these models are not very smart because they have no awareness. And this model, previous model, they don't understand whether the prediction is correct or not, or how wrong or how good it is, right? They're just very good in doing this thing, and we're gonna have to do something else later on to make them be a little bit more aware, okay? But I'm just gonna show you they can do kind of amazing things. Again, you can build these small scale intelligence. You can even do this for dynamical problems. So this is something more recently we've done, building models that can design proteins for unfolding behavior. So this is a classic experiment that Schulzen and others did back in '99, where they unfold these molecules, right? And so back there was a forward problem, took a long time experimentally. We've simulated this, many others have simulated this. What I can now do, I can invert the problem. So I can say I want a particular type of unfolding behavior, like here, and the algorithm will design sequences, multiple, there are obviously multiple options usually, to meet this particular design objective, right? So this is, again, another possibility. And then we can use this to you can see the very wide range of different problems, from designing a structure, designing dynamical properties, mechanical unfolding. We use this a lot of times for, making materials for food, actually, super strong fibers, plastic replacements. So this is anytime you want to design something new that nature hasn't invented yet. And actually, what these models actually do is and this is sort of shown in the middle here, this is what's called a blast analysis. It's basically an analysis. If you look at a sequence that we've designed, we ask you a question, how does the sequence relate to all the known other sequences that we have in nature, or at least that we've identified already? And so what you see is that this sequence we've made actually consists sort of like a puzzle or a new painting, right? But instead of using just a copy of an existing painting, it sort of combines ideas, motifs from different paintings, from different existing proteins to solve the problem of given the model. So this is pretty mind-blowing, actually, because it means that, again, through these graph representations, the model has figured out, okay, if I put these different pieces together, I can create this new property that nature has never invented, right? So these are new properties using, however, sort of the building blocks that nature has sort of evolved, right? So this is how we train the model. So we can really do new things. So we can discover new proteins. We can also, this is some new work we've done, sort of extended this to motions. So we can design proteins for certain motions. So if you want to, have certain, not only shapes, but dynamical shapes and how proteins move, we can design for that as well. So similar idea. We can do a really good job. So those are all things that, and to be honest, if you would have told me 5 years ago, we can do that, I wouldn't believe it, probably, right? And it's the same is true for protein folding, of course, and many other problems in this space. So these are kind of things we were imagining we needed to do, wanted to do, we couldn't really figure it out. And so there's a huge space in engineering, right? So you can do this at larger scales. These are some AI-generated spider webs. So we fed our own spider webs that we've scanned in our lab, real spider webs, and we trained AIs to learn the construction principles of how spiders make things. You can also teach it structural design principles in architecture, I presume, in civil engineering. And you can make, kind of synthetic analogs that look like real ones, but aren't real. We can actually do this for silk sequences as well. So it's pretty flexible, kind of, you can see, like you can design many different kinds of proteins, even classes of proteins, right? These are all silk sequences, and we can make very particular type of niche proteins in this field. And then you can make weird spider webs that don't look like real ones, but they use the design principle. So you can kind of think, see how this can be applied in your field pretty widely, because here I'm combining objectives that nature has not needed to, obey. There's nothing to do with evolution. But I can tell the model, hey, I want to make this infinite 8 or whatever it's called, this structure, and it will paint that structure essentially using the brushes of a spider web or microstructural materials, right? So this is a more classical example, right? So I want to get a constitutive law, and the algorithm will design microstructures for me. So this is pretty widely applicable. All right, so all of these models are, I think they're interesting and they're relevant, important, but again, they're not aware of their own predictions, right? So they really just make predictions, and it's up to us to, check the prediction, maybe go to the lab, build it. So what I want to do next, I want to talk about how we kind of bring this to the next level, right? So now we're going to think about, okay, now I have this prediction, but rather than just letting models make predictions, can we teach models sort of more structured reasoning abilities, okay? And that's what this picture sort of symbolizes. And there's a couple of different ways for which we do this. One is, of course, we can see that if you look at biology, both intelligence actually or material function, which is something we're more familiar with, of course, but is you build complex material functions by simple ingredients. Spider webs are great examples. I mean, you have really simple proteins that if you arrange them in a pattern and you make a web and you make an architecture, all of a sudden you create one of the most amazing structural materials known. And that is because these interactions happen in a very nonlinear, unobvious way. There are many other examples of intelligence, right? So ants and animals, civilizations, and so on. We create higher levels of intelligence by having collaboration interactions, both synergistic and adversarial relationships. So that's the principle we're going to use. And there's a couple of different ways you can think about building this out. So let's say you're an engineer, a scientist, and you created these different expert models, right? They can do protein design, and another one that can maybe analyze or predict a manufacturing process, and you have another model that can predict optical properties. And you can basically, the simplest way of sort of integrating them would be to have a gating function that would say, okay, what problem are you interested in? And then you choose, right, one or the other, okay? And that's one way, but it doesn't really create synergies between the different, because it's just a linear process of one or the other, right? So what we can do, though, is we can play with this idea and actually think, okay, so instead of just teaching the model how to choose one way of answering, we teach it sort of a recursive loop of thinking about the problem, okay? And so there's sort of 3 different ways by which we do this. The first way is this, where we have a model, we call it XLORA, and it doesn't really matter what it's called, obviously, but that's just what it's called. But the idea is the following. So you have a bunch of these, expert trained models, right? So you have trained a model that's good in protein analysis, math, and logic, and whatnot. And you then say, okay, I'm going to train this model to do all these things individually. So this becomes my basic building block, and I can train these models really well to do these individual things. Then I'm going to put them together in a larger model by doing an ecosystem of sort of interactions. And here, I'm no longer teaching the model how to solve this particular problem, but I'm actually teaching this model, this XLOR model, how to solve the problem, right? So again, I'm teaching the model, I say you have all these different capabilities, and I want you to figure out how to combine these capabilities to solve X number of problems. And that's, of course, a very different objective than teaching the model the answer, right? I'm not teaching the answer, I'm teaching how to get the answer by reorganizing the model itself. So beginning to create a sort of an awareness in the model, right? Sort of in quotation marks. Awareness is a loaded term, and I guess in AI, but you can begin to think, wow, this model now is it's running through the problem, and it's thinking about how do I best solve this problem, and then it solves the problem. And so it does sort of, we say, it does 2 steps. So every time you ask the question, it is not just answering, it thinks about it for 1 step or more, actually. In this case, only 1 step, and then it answers. And so the way this looks like visually is if you were to ask a question, right? And so you ask, compute properties of this protein, or tell me why this protein works so well. This is a visualization of how the model organizes its own structure internally. So these are using all the different capabilities in new combinations. So it uses, skills from mechanics, skills from proteins, skills from math, and it combines them in these new ways. Right? Okay, so this is what this model does. And it can do really fun things. Like it can actually, if you sort of look at what the model can do, it can, and it's hard to read a little bit, but yeah, you can do predictions. You can say, calculate stability of protein sequences. But you can also talk to this model. It can answer questions. So it can say, okay, so which one of those sequences is the best, the most stable? And then you can ask questions, why is it the most stable? And it will give you an answer, right? So it begins to connect the dots literally between the calculation, the reasoning, and why, the chemistry, and all this. And this is because, of course, this model has been trained on all these different kinds of data, right? So it begins to kind of put different things together. So this is sort of the first illustration of how we can build something like this. We can make this more explicit. So sort of the second stage in this is to say, okay, I'm not interested in just one thinking step. I can actually teach this model to do a very long thinking period. So instead of just reflecting on one token, one step, I can let the model reflect for a long time, and I can actually divide up this kind of process into thinking, which is basically a logical, sort of rational way of solving a problem. Like if you get a math problem, you would, you would say, here are my variables, here's how I can simplify the equation. oh, I have a PDE. Oh, okay, this is a tool. So this kind of step by step that you think about it. I can teach the model how to do this. And I can even go further, and I can actually also teach the model to reflect on its own reasoning steps. So I can basically let the model critique what it has done. And I can then improve on this because I can actually recursively, I can go back and I can say, hey, this is your reflection of your own thinking. Why don't you improve the thinking? And I can actually repeat this. And I can do this and I'll show a little more detail in a second, but I can actually do this with multiple agents. So I can have sort of, a model that does the thinking and the reflection, and another agent, another model that will basically really try to work against that first model and critique it really hard and say, hey, you really got to improve your thinking. Okay, and then look at it again, you can repeat this process. So you can do this within the model, but you can actually have multiple models play this game. And you can imagine if these agents have different objectives, you might get a really good result, right? Because if it's like in a team, if everybody on the team thinks the same way, you get an answer, but it's probably not the best. But if you have a team of people with different perspectives, different backgrounds, you're probably going to get a much better answer. And it's the same here as well. So I can deliberately sort of force the models to have these adversarial relationships by having multiple agents. And this is an example in natural language, how it would look like. So yeah, you give a problem like, why do hierarchical structures work so well? And a conventional AI model will just give you an answer, right? Say it works so well, blah, 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 because of this. Here, the model sort of develops the structured process to get to the answer, right? So it defines terms, it talks about benefits, gives examples, and goes on actually for a long time. It goes through a whole lot of different steps, including in some of the work that I don't show here, we do symbolic reasoning. So we teach the model to build graphs in symbols. So we basically do the kind of thing we did earlier, I showed you with the isomorphism. So we basically try to model to think in symbols. And when you do that, the model creates a much higher level of abstraction capabilities. Then it does reflections, or it might say, okay, clarify some things, but again, you can go back to iterate, improve the thinking, or you can give the answer. And so the answers you get, after this process are much better, right? So every time you iterate, so this is sort of an iteration. So every time you iterate through, you get better answers. So they become more comprehensive, more clear, but you pay a price, of course, and that's compute, right? So because every time you do that, you have to integrate over more steps. The other thing I want to mention is sort of how do we do this actually? And this is sort of the secret sauce here, and that is the following: if you teach models conventionally, you teach models sort of here's the answer, right? And that was okay in the beginning because you want to get the model some idea of how we think as humans, let's say, how do we solve problems, right? But then what we really want to do, and we call it structured thought training. So we basically teach the model, here's some examples of what I think is a good way of solving these kinds of problems. But then what I do in a second stage of training, I say, yeah, now I taught you, sort of how I think. Now I want you to give really good answers, but I'm not going to tell you how to think. In fact, I'm masking the thinking. I'm not going to tell you how I got to the answer. But I want you to come up with your own way of thinking, right? So this is done through a process called reinforcement learning. So we basically teach the model to get the correct answer without training the process of getting to that answer. Okay? And so this means the model has to figure out its own pathway to get there. And this really then allows the model to learn essentially on its own. And there's another sort of twist to this is that the model actually generates these answers and questions on its own every training step. So in traditional machine learning, you have training data, right? Here, I have ground truth data. It might be books, papers, expertise. It might be a simulation engine. But the model at every training step actually on its own generates a question and it generates an answer. And it generates an answer on its own capabilities at the moment and a perfect answer based on the ground truth, like reading all the papers and stuff like that, or running the simulation engine. And the training objective is not just the answer, it's actually the difference in quality between the answer it can currently provide and the ground truth, right? And so as the model becomes better, the model actually, the model becomes better. So the differences between the correct answer and the current capabilities become smaller and smaller. So that training objective becomes increasingly difficult. And so the model actually doesn't, in fact, see during the final training stages the final answer. It only sees the difference between the answer that it can generally generate and the ground truth. And so this objective forces the model then to create a sort of solution strategy in these mass tokens. Anyway, that's a little bit more detail maybe than you wanted, but that's really, really exciting because I can let this run forever, right? And the model will basically just teach itself, and I don't have to worry too much about data. I mean, I have to have some ground truth, obviously. So the third step in which we kind of so let's say you can make models that are pretty smart and they can create pretty good, well-reasoned answers, but you can also then sort of take multiple of these and put them together in a group. Rez really referred to this as multi-agent modeling. So we basically take a bunch of models, and each of them might be, could be different things actually. It could be a classic AI model, it could be a language model, it could be a finite element model actually. It could be a model that can write code and execute code. And I can then sort of put these agents together to solve a problem. Okay, so this is what we refer to as multi-agent modeling. So here I've done this sort of experiment here where I gave a problem like, create an inner potential. And this is an example I want to highlight. So this model has never been trained on the energies of these oxygen molecules, any molecules. Okay. So if you ask the model, if you ask a conventional machine learning model to give an answer, it will hallucinate an answer. It will tell you, oh, that's the answer. What? Totally wrong. Here the model understands, I don't know the answer, but I know a pathway to get the answer. And the way the model chooses to get the answer is to write a code that runs a quantum mechanical DFT simulation for different spacings of atoms. And thereby, it creates the data on the fly to solve the problem. And so this is sort of the strategy behind there. Okay, and so we can do this actually for pretty large scales. So I can do this for toy problems like I've showed you, but also for real problems like protein design. So we've built very large agentic models that that solve protein design problems. And if you look at this particular setup here, you can see there's a whole bunch of agents, planning agents that plan the process, critics for the adversarial relationships, assistants that have themselves a set of agents available, including a variety of AI tools. So those AI tools that I talked about earlier, like these expert models, right? They can be part of that spectrum. And in fact, when we did this paper, we created this forced GPT model, the protein design model, OmegaFold, like AlphaFold can be a part of that. And then when we were working on this, actually, another AI model came out called Chroma, which is another generative design tool. And within an afternoon, I could add this new capability to this agent system, right? So you can very quickly see this becomes a whole ecosystem of AI, right? And so, of course, to develop each of them is going to take a lot of effort. So one lab might be spending years and years developing one of those tools, but you can also integrate them, and you as a lab can integrate others. So we do everything open source, of course, and everything is shared through Hugging Face and GitHub, of course. So it becomes very easy in the community. This is how machine learning AI sort of generally has evolved very quickly, because we can share things and build on each other's work very, very rapidly. At least those who work in the open source community, which most of us do, but some companies don't. But most of us do, I guess. And so yeah, you can really supercharge this. And so my system now, you can use this and build your own thing out of that, right? So this is sort of how progress becomes very rapid. So it's sort of a little bit difference, I think, in some of the other conventional simulation areas where sharing tools, yeah, maybe, but it's very hard to connect them. But we building everything in ecosystems like Hugging Face, PyTorch, that make it really easy for anyone to add to the code, change things, and so on. So a few other things, I don't know how I'm doing with time, but yeah, a few minutes. So a few other things we can do. These models can, so when you build these agent systems, you want to really create capabilities. One of the capabilities you want to make, for example, would be a vision capability, where you can make, let's say you design a protein, run an MD simulation, and you want to look at the results, literally, right? So you don't want to just feed the model trajectories of thousands and thousands of frames. But I can also train models, and this is one of the models we've developed. You can show them pictures of proteins, and these models can say something about these proteins, how they behave, because they've learned to understand how proteins look like and how that relates to structure and function. So those are vision models. And again, they work in the same way, except in these graphs, the nodes, right, aren't just words or variables or numbers, but they're basically pixels or groups of pixels, right? And so they're very flexible. And this is why these models can make a connection between a pixel in a protein image and language and reasoning and explanations and things like this. And you can, of course, also teach these models to make new images. So here's some of my favorite examples of sort of these crazy things, like we say, oh, take a look at a pollen particle. And I want to look at this pollen particle, and I want to design a new microstructure for a fracture-resistant material, for example, right? It's the kind of stuff that, yeah, you really needed a human for, right? Because I can take a look at this pollen and I can understand, yeah, I can't use a pollen by itself. I need to make a periodic structure, right, to make a material. And yeah, but this model figures that out. So this is sort of why I see a lot of potential, right? So not only can you reason over images and video and all these other things, but I can also make new images. I can create designs. Like these are some fun things we've done. Some of my students are architectural inclined students, and so we created this, kind of. You can see the conversation. So this is sort of a multi-agent conversations where the agents basically talk to each other and ask questions, and then finally they come up with a design. And so you can create really interesting things by combining ideas and concepts from different areas that are not necessarily connected. Come up with these. You could also make 3D. So this is sort of more like a survey of stuff you can do, which I thought maybe it's interesting for you to see. So we can make not just images, we can make 3D meshes, right? And then you can of course take these meshes and 3D print them. And so this is just one illustration. So this was kind of a hybrid of a conch shell and a leaf microstructure. Right? So this is what the AI model has been tasked to do. And so it came up with that design, the architecture, and I can print it, of course, as well, and I can make it. I can also reason over physics problems. I can ask the question. So yeah, not just proteins, but I can say, here's a two fracture scenarios, which one's tougher? What's the mechanism? How can I improve it? So you get the idea. So this is really powerful. And so these are all models that we have developed ourselves, trained them. You can train them. You can further train them. They're all available on Hugging Face, open source. One of the things we've done with this model also is to create a sort of a very specialized model that would predict whether or not a crack would propagate. So we basically show this model a picture of a crack in a boundary condition, like this stuff on the right on the top, and we ask the question, what happens next, right? So will the crack nucleate? And if it nucleates, how much damage will be incurred? And so the model can predict that as well. So those are some really, really interesting things. And of course, you can see applications in autonomous experimentation or in predicting properties. Or we can teach this model to actually predict a movie, a trajectory, right? So instead of running an MD simulation, I can actually produce a movie. So the sort of frames in a movie. Actually, I don't think I have the movie here, but these are the frames in the movie. And you see the model does a really good job compared to the MD. This is trained on MD simulations. So there's a lot of different things you can do to kind of model physics. The last thing I want to show you is how we model the discovery process itself. So like in scientific discovery, you might be interested in coming up with a new theory, a new hypothesis, maybe. How do we do this? Well, so again, we come back to graphs, but now what I did here is I basically took a big stack of papers, thousands of papers, and I use AI models to build an ontological representation, like the category theory we talked about earlier. But instead of doing it internally in the model's sort of hidden dimensions and its abstractions, I'm doing it in natural language. And so these graphs essentially, I think you can probably read it. Well, it's actually not readable, but I have some later examples where you can read it. So it describes essentially all the relationships of how phenomena in these papers are discussed. So thousands and thousands of graphs. Now, they can all be connected. They're merged into one gigantic graph. So this gigantic graph sort of looks like that. So thousands. This is actually not the whole graph, but otherwise you wouldn't see anything on the screen. But it's a part of it. But it's a highly connected system of interactions. And so what I can do with this, I can kind of follows exactly this idea on the right? So these simple things. But now, maybe here's some connections there. You can kind of see, I don't know if you can read all the terms, but basically these are all terms and concepts and the relationships between them. And it turns out if you train this on a large data set, it actually forms a really well-connected graph because, of course, concepts are connected and they're transitive, right? So if one paper talks about, let's say, sustainability, and it talks about creating sustainability out of plants, maybe like in this building here, and another paper talks about plants, and it talks about plants and the connection with fungus and mycelium, now you have a path. And even though the original papers did not talk about connecting plants with mycelium, because of the transitive properties, they will be connected in this way. And so I can actually use this to create scientific discovery engines, basically. And so these engines are able to sort of connect a lot of different ideas in answering questions or creating new hypotheses. So like here, I'm giving this model sort of this challenge and say, find me a path between, let's say, mechanical properties of sustainability and mycelium. And it will build, it extracts a subgraph out of this gigantic graph that tells me all about the relationships between these ideas, right? And so now I can use this and yeah, either, like I said, either answer a question or create a new hypothesis. And so in this particular paper here, you might have seen it. It's we call it Psi-agent. So we used a multi-agent system, basically, this agents, multiple AI agents, to think about this graph. Okay, and so in particular, we create this graph, and then we input two concepts we want to connect. And we can even pick them randomly, so they're totally unbiased. Right? So two combinations of weird things. We ask the model to find connections. And in fact, we sample all possible connections, or the obvious ones, which are maybe the direct path, but we can also sample paths that are not direct. And this is sort of how we make discoveries. We kind of have these random permutations in how we connect different ideas. So long story short, so this multi-agent system basically negotiates these solutions. So it sort of works on this problem as a team of AI agents that recursively, repetitively go through this process, identifying paths, assessing them, assessing the quality, assessing feasibility, and ultimately they provide an output. And so this is quite remarkable, because this sort of structure that they create is determined autonomously by the agents. So we don't have to tell them, do it like this, but they come up with the structure by themselves. So they kind of have they create themselves a graph of interactions between the agents. So you can see I'm really enamored by this idea, because the world really is kind of organized in this way. So the agents basically decide how they interact, and they each interact with the graph, and the graph itself interacts internally with the model. So it's a really interesting way to think about the world. And this, creates, for example, research ideas, hypotheses, and then we can, of course, let this loose on solving this. So this, we have not done this yet, actually, but you could define problems. So each of those I should mention, so the kind of details, so the model comes up with these very long documents of about 10, 20,000 words. So these are very detailed proposals, and they cover kind of all these different aspects. You can take those then and give them to one of the other agent systems to solve the problem. Right? So this is sort of how you can automate the whole process. So again, we have not done this, well, we've done the lower part, but not connected the two. Right? So but that's something you can do in principle. It's very scalable. Oh, wait on. But it's scalable. I mean, I can let this engine run in parallel. I can generate thousands, 10,000s, hundreds of thousands. So if you have big compute, like if you have a nuclear power plant powered, cluster, I can generate hundreds of thousands of new research ideas, and I can scale the data set too. I can scale the data to all papers written, or all the internet, and so it really is something that of course humans cannot read all of these, and so we can rank them actually. And so we have algorithms that rank all these different possibilities by novelty. So we have an agent actually in the Psi-agent system that basically scours the literature. So it comes up with an idea, and it assesses how novel the idea is and how feasible it is by comparing it against literature. So all of this can be totally automated. Right? So, and of course, in the end, you can maybe pick the top. Now it works again. It's kind of amazing. Anyway, it works again. My clicker works again. So in the end, you create outcomes that you like. You can let the model even make you a drawing of the material, and even a process of how to make it. Right? And the model can actually tell you what these components are and what they mean, right? So the model has an awareness of what it has made. So it's not just like randomly producing some garbage. It's actually, it understands why it's there, what it's there for. And it's very detailed. So it's just a snapshot, right? So detailed chemistry. So the quality of these predictions is pretty high. And even do manufacturing. And you can do other fun stuff with AI. Of course, you can create connections between different areas. And I just want to show that at the end. You can connect things like music and materials. But many of you have talked to me about this today, actually. So we've used some of those multi-agent AI models to create these transformations, right? So for example, converting proteins to music, but not just literally mapping note sequences, but actually mapping structural functions. So what that means is basically creating a coded representation of music as a protein, so that if I have a music piece, I can make it into protein, and nobody knows the protein is actually music, but I can convert it back, right? And the other way around. And so I train models to make these translations bidirectional, and they can discover these rules completely on their own, right? So it's like creating a coded language. And in some work we've done some artwork with this, or some music compositions. I don't know if it's going to play. We can actually recursively play this. It's actually playing on here. I think you can hear it, where you can create. This is a little more complex process, but it's a recursive process where we start with a small protein, translate it into music, and repeat this process, fold the protein, and when we fold the protein, basically adding new vibrational modes to the system, and so the music becomes more complex, and the protein becomes more complex. And so the whole process sort of creates iteratively complex representations of the system. So anyway, so that's some fun stuff you can do. So you can do a lot of really problems, I would say, that are, that seems totally, unsolvable, obviously, both in science, but also some obscure areas, like what if you could find the hidden language to translate music to proteins and the other way around? I mean, these are all things that, you really couldn't do without these tools. So it's a pretty exciting time. And yeah, hopefully I've shared some of the stuff with you and you enjoyed it. So happy to answer questions. Thank you.
Take 2 or 3 questions. We're a little over time, and then we have a reception, so there'll be plenty of time to chat with Dr. Buehler afterward. I see lots of hands. Jackie, go ahead.
Yeah, so in your models, in a complex system, there's with a lot of nodes, a very large space of possible graphs. How do you select a graph? I mean, from among all the possibilities, what kind of algorithms do you use?
Well, the graph is actually, the graph is constructed by the model. Right. So we basically show the model. I showed some of the training strategies a little bit. So we begin by showing the model sort of different tasks, right? One would be kind of denoising task. Like you can say, I want to do show it sequences, and I'm just going to mask out some part, and I'm going to let the model figure out the gaps that I've crossed out. So this forces the model to create a structural representation internally about how the sequence works. Because if you cross out one of the letters or you remove part of the solution in a boundary value problem, there's something that's missing. You need to understand how to do that. So it builds these graphs to solve this problem. And then because you do this for a variety of problems, for a variety of tasks and solutions, the more the better, because it means the model is forced to learn more general principles, right? So and there has been work that showed that actually, that let's say in language models, for example, if you have concepts of empathy or concepts of sadness or happiness, their structural activations, isomorphic or mappings in the graph that are learned to be activated to represent these features. Right. So this now, of course, I say this because it's hard to mine that. I showed you a bunch of the graphs. These are just sort of subsets of thousands and thousands of graphs the model generates. It's very hard to understand what the model does in the graph space, but the model essentially does that, and it learns these structures to think in those contexts. And then in the natural language representations, you can actually read it and understand it. That's why we do that, because you can understand how does the model solve the problem, but how does it manipulate math and do algebra and things like this. And so there you're actually dealing with sort of letters, and you can read it yourself. Yeah.
But there's nothing like an MDL minimum description like score or anything that's used to compare alternative.
So no, but the model has to figure out. So the model is actually learning an operator, so that the model has a certain capacities. I don't know what the MDI what it is, but actually, but let's say you have a certain set of parameters, right? By teaching the model cannot just memorize everything. So it has to find a way of compressing the information, and so it has to find a way of creating more generalizable descriptions. However, that doesn't fully get you there, as I said, because if you do this, still the model will try to memorize. So that's what we do reinforcement learning. We teach the model not to memorize, but we teach the model more of the principles of how to get to the end. So that's why I showed sort of towards the middle of the talk. But in principle, yeah, it's all about teaching these relationships, and you want to give the model a wide variety of tasks, so the model sort of cannot just memorize, or you do additional techniques like reinforcement or masking or there are strategies that people are researching right now to get to that. Yeah, but there's a budget essentially of capacity you have, And there's also, I didn't show the details, but in the construction of the graph, you actually you normalize the edges, the weights of the edges, so that the model cannot create very, very strong edge connections. It can only create edge connections between 0 and 1. So that's another really important budget, because it means the model has a certain budget of connectivity, and it can't cheat. So it can't just say, oh yeah, I'm going to memorize this connection. So it has to formulate all these relationships within pretty sparse graphs. So you saw the graphs, right, in the picture, they're very sparse. And we can actually, so in one of the models, in this particular model I showed, we can actually even control the sparsity of the graph. And so we can also make it learnable even, so the model can simply learn by itself. We can provide regularization terms, and we basically force the model to have very sparse graphs, but still perform well. So you can put this in your loss function. So there's a couple of tricks like this you can add. So there's a lot of things. Yes, yeah. You can penalize the model for making graphs too dense, for example. This is things like this, yeah, you can do, yeah.
You want to ask? Go ahead.
Yeah. So I guess like my question has like two sections. One of them is that most of the data you show in protein engineering or protein work in which has a lot of data already, like many back from many years, but material science in general has like a large parameters with like very small data when it comes down to other materials.
Right.
How do we like combat that? And another question would be, most of the published work is like actually showing relationships that had work and what we are looking for, but they don't really show like the negative
Right.
results or things
Yeah.
that hadn't worked. How this models can actually like predict relationships, but also knows that that wouldn't maybe work because
Right.
like it hasn't.
No, it's a good point. Yeah, so the first thing, there's data on proteins, but actually there's very little useful data actually still, because we have sequences, but it's like having, solutions to problems, but we don't know what the problem was. It's actually like in engineering, you have a bunch of different designs. You could look at every building, every design, every thing ever created. You might not know how, but we have the design. So it's equivalent to proteins. We have the protein sequences. We don't know why they're made and how they function. But in engineering, yes, generally it's more diverse, the data. You have like, textiles or plans and all that, but you can still follow a similar approach, right? You can teach models to look at solutions to, fabric designs or plans, and you can teach them not the solution objective function, but you can teach them principles, right? And then the data actually, like in proteins, we don't need a ton of data actually. If you have a well-trained protein model, you might only need a couple hundred examples. It's actually very little. And in engineering, it would be the same thing. And we've done engineering problems too. And at the end, so negative examples is an important thing. If you don't have negative examples, that's a problem. And that's why, at the end, we in the multi-agent system is partially there for that, because it's just like we would work. If you have only designs that worked, to really check whether the thing you've created or the theory you've proposed, you have to do an experiment or run a simulation. So that's why we built these models with the ability to have physics-based simulations, or do an experiment even. If you have an autonomous lab, or if you have an ability to run an experiment, models can design an experiment for you, and it can say, hey, I want you to run this experiment, and then I can see. And when you do that, then you get more data, and then the model can reason over the old data, the new data point, and it can kind of improve prediction. So it's this iterative process. But yeah, that's very much part of the thinking process, that you have an iteration, and you might have to collect data. We like to make things more simulation based, because experiments are very expensive. But we do a lot of work with experimental collaborators as well, and you can feed that back to the model. But yeah, it's the other thing I want to say is that surprisingly, there are a lot of areas where you can translate knowledge. So that's a really totally unexplored area. Like there are maybe, in proteins, there's a lot of knowledge in proteins. Some of those principles can be very efficiently applied in other areas. You can translate, these, because of the very high abstractions the model internally create about how things work. And that's been shown in language, in translation. Like you can teach models 99% in English, and you give it just a couple of examples in other languages, and the models are perfectly able to translate all sorts of languages to one another because they've figured out they can generalize. And we're just at the cusp of doing that and just understanding that and scaling that. But I think that is something that we already know in other areas. And in sciences, of course, science is a little bit behind because there's not, I mean, the kind of investments, that, Meta and OpenAI have, I mean, hundreds of billions of dollars, trillions maybe, and then you compare that to the budget of even, the entire science budget of the United States and the NSF, DOED, and combined, I mean, it's like opposite, right? So yeah, I am obviously advocating to get sort of a big Manhattan project in, let's really, supercharge AI for science, but it needs resources. So we can do things in academia on a small scale and build sort of foundational models and ideas. But if you have resources, you can scale this to, I mean, pretty significant. And actually, I think it's going to scale better and in a more controlled way than many other areas because we have a lot more control. Yeah, the limitations, like you said, but in science, I can do an experiment. I can actually validate. In a lot of other general AI areas, like if you want to teach models to reason and do philosophy, it's hard. There's no theory, right? It's like very, very difficult to create AGI. But in science, we have a lot more things to ground ourselves on. Even if it's just, like I said, mass conservation, right? I can just do mass conservation. I can say, can check, is this protein going to fall apart? I can run in a couple of MD steps and see, is this protein going to fall apart or not? And then it's going to give me a signal. Is this the right direction, right? So I can do tricks like that that are totally what we would do as scientists, right? We would say, yeah, let's get some initial feedback. Yeah, so I think it's actually easier, but yeah, it takes resources. Yeah, but it's definitely scalable.
Awesome. In the interest of time, we're going to transition to reception afterward. Let's thank Markus one more time for all.
Thank you so much. Yeah.
Yeah, I don't know why.